Good afternoon, guests. I'd like to welcome everyone to the Future of Radiometric Level Measurement digital event with Gerhard Jansson, our level expert from the application support team, and Francois Gagne, the product manager for level, temperature, and pressure from the marketing team. If you have any questions, please put them in the chat area and they will be answered. Also, before handing over the reins, we're going to do a poll, and I will launch that right now. I will give you a couple minutes. We'll just wait for a few more people to enter, and then I will hand over the reins to Gerhard.
While we're waiting, gives me a chance to do a quick introduction. Bonjour tout le monde. Merci d'être là aujourd'hui. Thank you everybody for joining us. Much appreciated. We have some very exciting content for you all today about radiometric level measurement. But first of all, we'd like to know more about you with this poll, and gives us a chance to warm up a little bit. By the way, you can put your questions in the chat while they're on your mind, and we'll end a question and answers session at the end where we'll go to your questions. So feel free to type them as they come to you, and we'll try to get to as many of them as possible at the end. And those questions that we can't answer, we'll send a follow-up email with a copy of this presentation and answers to the questions we haven't answered. And this is being recorded also and is made publicly available on our website. So if you liked it so much that you like to watch it again over Christmas time, you'll be able to do that, or to show it to other people if you want.
Okay, I'm going to give you guys about another minute or so to answer the poll question.
And I see more people are joining. That's good. And I apologize in advance for those that were there last week when we did radar and solids. That first part about Endress and Hauser will be the same, so it will be a refresher for those of you who were there, and new content for the new people joining today.
I have now shared the results of the poll.
Okay, so yeah, lots of people interested in radiometric level measurement, and lots working on measurement projects. That's good. People interested in ENH, that's good. And people who just like webinars, love it. All right, well, we have a good one for you today, so let's get cracking. So Gerhard, you will be the slide master.
Yeah. You want to go to the next slide?
Or to the first slide? We're still
just a moment. Yeah, just a moment. Just a moment.
Okay.
Should be back to you. There you go.
There we go. Okay. So yeah, next slide. That's what we're doing today. Radiometric level measurement, and focused on our new Gammapilot FMG50. But to start, I wanted to introduce Endress Hauser, the company, say a few words about who we are and where we come from. And that's ENH in figures. Company started in Switzerland back in 1953. Actually, the little here we put a dash, but normally it's a plus sign. That plus is also represents the cross in the flag of Switzerland, because it's a Swiss-based company. And yeah, an important figure here, the 7.5% of our income that we spend every year on research and development to bring these new products to market. We like to be on the leading edge when it comes to value added, when it comes to technology. We're known for excellent quality and leading edge technology. So we like to keep it that way. And we have 8,000 patents and patent applications showing for it, and growing every year. So we are a global company. You can buy Endress Hauser instruments, solutions, and services in just about every country in the world. We have 14,000 employees and growing. But we still follow the guiding principle of our founder, George Endress: first serve, then earn. That means we focus on long-term relationships with our employees, with our customers, rather than meeting the monthly profits, the quarterly profits. And we do the right thing for employees and customers, and we believe then success will come naturally. And these are our owners. So 3 generations of the Endress family that you see here. On the right, Klaus Endress, son of George Endress, the founder, who's still president of the board. And I say the word generations. So that's an important word for us, because we think long term. That's our time scale, is generations, not a month, not the week, but keeping a company strong long-term relationships that will last generations. So even though we're a global company, we're family owned, we're privately owned, and we still have strong family values that guide our actions, especially in the current situation. We saw proof of that when we were able to keep our employees and keep our commitments to our customers, to deliver value for them and the level of service they expect, even though there was this, we're in the middle of this pandemic crisis. So yeah, that was just a brief introduction on who we are, and now we can move to the core of the presentation with Gerhard and Radiometric.
Good day, I should say. And yeah, I'm also bilingual, but my French is not that good. My Swedish is though very, very good. So English and Swedish, so IKEA language, and the English will probably be my way of communicate. Anyhow, so we are going to spend the next 45-50 minutes on talking about Radiometric. And this is first of all just to show the product offering of Endress Hauser when it comes to level and pressure. And as you can see, there's a lot of these yellow devices, which is then the nuclear source containers. So we have them for continuous measurement, point level detection, interface, and density. And density is by far the most common here in Canada. And next slide just show the evolution that we have went through. We started in 1962. I was a very, very young boy at that time. And now we are 2020. So the last one that we have introduced is the Gammapilot FMG 50. So we'll talk a bit about that, and we'll also talk a little bit about applications that we do. So this Gammapilot, or the transmitter that we are using, it looks very much the same, whatever now this is for point level, continuous, interface, or density. The part that will change will be now the active part. This length here is of course then depending on the type of application. So we are going to talk about a little bit about how can we save time, minimize engineering and installation effort. And one of those things that we're introducing now is loop-powered instrument. It's a true 2-wire loop-powered instrument. Next thing is, of course, increased plant safety and efficiency. And plant safety, of course, have different meanings, but this refers then to SIL. If that is now something that you are looking into, we talk a little bit about that. The other thing that we're also going to talk about is verification and continuous monitoring of the health of that device. We are then talking about heartbeat technology, and I'll go into that as well. And then there is some additional things like increased temperature rating of the device that will have an impact on if you need to do any kind of cooling effect or effort or anything like that on the new Gammapilot FMG 50. So looking first of all to the loop powered. So this, as I mentioned, it's a true loop powered instrument. The previous generation, they have always been 4-wired, or they have had a separate transmitter, and then of course also those will have been 4-wired. If you now can do this as a 2-wired instrument, it will make some cost savings. Namur is something that you probably recognize. This is an organization amongst the chemical companies in Germany, at least it was starting there. WIB is a user organization in Holland that do evaluations of instruments and so on. And they estimate these kind of cost savings if you can do a loop powered instrument installation instead of a 4-wire. So really cost saving, plus usually it's also easier to do the installation. So if you now look to this picture, we can then see the reduced effort, because this will be a 4-wire device. Of course, you have power supply, you have the 420 milliampere communication to each of those devices. If I now will have a loop powered instrument, I would then only need 1 pair of these cables. So of course it will be a reduction in terms of wiring costs. This can be general purpose, intrinsically safe, as they say down here, as well as explosion proof devices. I'm then talking also a little bit about where the animation doesn't really work out. Some of the internal parts of the sensor that we have patented and will actually give us some really feature, but this animation doesn't look to work, so we skip that one. So this is talking about high voltage, and I'll explain that a little bit later on here. And then how the scintillator is working. So to achieve now loop powered, we need to do something. We need to reduce the energy consumption of this device. So a 4-wire device, if we would compare this to a light bulb, it would be like the old style or old time light bulbs. The new FMG 50 would in comparison be like those new LED light bulbs, a lot less energy hungry, and by that we can also then make this as a loop powered instrument. There is also other benefits that I will come to that we also can achieve by having a loop powered instrument with a lot less energy consumption. So this is how we did it in the past. We had 4-wire connection, power supply, 420. This would be an active output in that case. If we now look to a loop powered, this is of course now a passive. It's only a 24-volt power supply, getting back the 420 milliampere signal. So of course, if you're going from one to another, you need then to change the input from an active input to a passive input on the PLC or the DCS. No additional power. So once again, a lot of cost savings there. We can also look to other applications where there was maybe a separate transmitter used, which would of course also require a 420 milliampere, would provide a 420 milliampere output, but will also require an additional power supply. And then we had this connection to the detector itself. In most cases, if we now would replace this with a loop-powered instrument, this cable would probably be at least 2 wires, maybe 3 or maybe even more wires. These, in the absolute majority of all cases, can be reused if now so wish, and then you would just extend it over to the 4020 milliampere output from that remote transmitter and then into the PLC or the DCS. So that could also be a cost saving, that I don't have to spend additional cost on putting in new wires. Talking about then safety. When it comes to nuclear, safety is one of those things that is so important. And safety means, of course, many different things. It's a safety for radiation, that we keep the distance and so on from the isotope as much as we can. We usually don't really want to stay too close, even though that is usually not too harmful, but still this radiation. So of course we try to be aware of that there is radiation around, and by that we will also always have warning signs where the source is installed. But safety can also be according to SIL. So this device is now, of course, designed according to IEC 61508 to be SIL2, or if you have 2 of them, it can be SIL3. We work now in close relation with this third party TUV, which is a German organization which is seen by these involved in SIL as the company that do this certification for us. So this is of course now to protect people, plants, environments that we maybe use SIL classified devices. If you now would do SIL, that means also not only a safe device, it also means that you need to proof test it on a regular basis, whatever now that is, each year, every second year, or whatever now time period is. So what we try to do now is to make this proof testing very simple. In that regard, we will then use Device Care, which is a free software from Endress Hauser. And in principle, there is a wizard there. It's referring to SIL wizard that will step you through the whole process to do this SIL configuration and activation and the proof test. So in principle, what you do here, first of all, you need to unlock it. If it's already in a SIL mode, it's locked, so no one can go in and tamper with it. It will unlock. You can do the proof test, and then afterwards you lock it again, so no one go in and tamper with it. Of course, when you talk about SIL, it's a lot of different things that you need to go through, but this is now guided with this wizard, and in the end you get a report saying that this is compliant. Heartbeat is something a little bit the same thing to improve the safety, but we'll talk about that here. So heartbeat for Endress Hauser is something that you find with many of our instruments today, and it's in 3 parts. It's a part called diagnostic, verification, monitoring. And if we then look to the diagnostics, this is something that is going on 24/7. It's going through the instrument, check its own health, and going through a number of diagnostics, in this case 54 of them, and very much checking the health of the instrument. We of course want to see a symbol, and I'll get there, which I don't really see here. It's the check mark, the green check mark. If that is shown, it's good health. Any of these other symbols showing up, then it requires some kind of activity. If it's not a failure, out of specification, maintenance required, it will come up one of those symbols, plus also a diagnostic code, a little bit of a help text telling you what need to be done. This is of course according to the NAMUR NE 107. standard. So in this case, this happened continuously. There is no need to do really anything. So this is just something that we verify the health on a continuous basis. Now, in some cases, you might say that, oh, I want to have some kind of a verification that I really know that this instrument is as healthy as everything indicates. So I can now do a heartbeat verification. In principle, I start this sequence, say that please run now a verification, and it will then go through this, and it will then go through a number of different parameters. It's a pass-fail part to some extent. There can also be those that is actually giving you values. For instance, sensor temperature allowed between -40 and +80. Right now, in that case, it was 19 degrees C. It will then be on that verification report. These are the actual conditions right now. So there is sensor temperature, pulse values, and so on. Down here at the bottom is the expectation of lifetime for the photomultiplier, how long time we can expect the source activity to last. So these are things that then can be used in the monitoring parameters. So jumping then into heartbeat monitoring. So we will look for the photomultiplier, which is a big part of the detector, and I'll come to that more in next slide. And then, of course, the expected lifetime of the isotope itself. So this is probably also an animation that doesn't really work out. So anyhow, this part here is the active part where we have some kind of material, either PVT, which is polyvinyl toluene, or sodium iodide. It's a crystal which will convert radiation to light photons. Light photons will then go into the photomultiplier, which will then count them. They will be amplified and counted. And at the end up here would be then a converter between number of counts and then a conversion to the analog output. So that's the photomultiplier, gamma radiation, and that is the high voltage that I was talking about before. Because the high voltage is a part of the detector that is very important, because through that we are going to regulate this high voltage, and it will then also compensate for if you have very high temperature or low temperature here, and also aging on this scintillator material. So we run typically in the low value, and eventually over time you are going to get to higher and higher value, and when you exceed 1200 volt, the detector is probably then gone and need to be replaced. But this is of course a way that we can now see how much of life expectation do we have still on this device. And that is, of course, temperature is one of them. It's also the number of years it has been in operation, but it's also a matter of what kind of radiation level do we expose the detector for. So at the bottom here, you see number of counts per second, and here it's number of years of life expectation. There is one curve for the sodium iodide crystal, which is typically used in density applications, and the red curve is for the PVT that is used for switches, continuous measurement, interface, and also to some extent into density applications. So what this shows now is the relation between life expectation and the number of counts. So if I now have a relatively low number of counts, and this is now an average number of counts, like 10,000 counts, I can now expect that this is going to be around 20 years of life expectation. So in my case, it would be good. I would have retired by that time, 20 years from now. So it would be a good time. If I then have a higher radiation to my detector, it will then generate more counts per second. And now I will then have a lower expectation. And as you see here, if I now have a very, very high dose rate, I will really decrease the number of life expectation. So this is important to kind of be aware of. And this heartbeat monitoring make it very, very obvious, this kind of relation. Isotope is something that we always have. We will always have some kind of radioactive isotope. Very often it's cesium, sometimes it's cobalt, and we know that after a certain time, we will have half of the radiation available. So we're starting with the original. After a certain time, we are going to have 50%. It's the half life value. And if you look now to cesium, it's 30 years. And for cobalt, it's a little bit over 5 years. So can I then expect an isotope to last for 30 years if I have cesium? Yeah, it will last, but it's a question of will it be useful and will it be accurate? Because it has some influences. So less radiation is less counts. And of course, then they can then have an influence on the performance of that device. In that case, we are looking to the number of count difference between, when we talk about the level between empty, when we have the most radiation to the detector, and where we have full, when we have more or less no radiation at the detector. As time goes by, this difference are going to decrease. And what you are going to start to lose is the ability to measure down at the bottom of the vessel. So that is going to give eventually, and then it's a matter of how long time. So this will give us an idea of how well the instrument performs. On the level switch, we have something else, but the difference is smaller, and it might be that just that you need to kind of adjust that again, and it still would probably work well. If we then talk about density, density is slightly different. First of all, we need to understand that the detector can be either a sodium iodide crystal or this polyvinyl toluene plastic material. And sodium iodide crystal is more stable than a PVT detector is, so that will have an influence on the accuracy. But we also need to understand that radiation is something that will decay over time, but it will not constantly decay. So it will actually fluctuate quite a bit. So therefore, we're typically talking about a fairly long integration time. Usually by default, we would have 60 seconds damping time on a density application. And usually that is not the problem. There is very few density application that I know of where you would have a big change just in few seconds of the density. Usually these are changes that happen over a longer time. So 60 seconds damping time is usually not the problem. Anyhow, so these things come then into effect, and then we can use this heartbeat monitoring. We can then look at the performance of the detector, of the isotope, and then we look to what kind of accuracy can we get on that particular device. Of course, as the isotope decay over time, this is now going to be a little bit higher deviation than we had initially. So that can give us an idea of what kind of performance we will have. So that was talking about heartbeat. Additional thing like cooling and so on. We talk about that. So it's a question always, is this important? Depending on your application. In most density application that we come across, which is usually on slurries in the mining, temperature is usually not a big concern, but there is other applications. And in the past, and also from other vendors that have a nuclear detector, there is usually a temperature limitation of 60 degrees C, sometimes even 50 degrees C. If now the ambient temperature is higher, it will then really reduce the life expectation of that detector. Now with the new design, we actually have the ability to go up to 80 degrees C ambient temperature around this. So if I can now do this, I eliminate all of this with water cooling or air cooling or whatever now, which is usually a big issue because you need to have pumps, valves, piping, controlling the amount of water going and used for the cooling. And of course, in the end, it's coming down to quite a bit of money. So if I can reduce water cooling, it's always a good thing. Another thing that we also spend a lot of effort on is commissioning. How can we commission a device effectively, safely, and so on? And one way of doing this might be this with a cell phone or another iOS or Android device, and you just use Bluetooth in that case. And I'll show that a little bit more here shortly. We can also do this configuration through a display, a remote display, or we would do it through a laptop and device care and then use just the configuration tool there. If you now look to Bluetooth, why is that so interesting? Because more or less everyone have a phone. And in most of these applications where we come across, there is really no hazardous location, so a phone can very well be used as a tool. Excuse me. And what we try to do is, of course, avoid to be in the vicinity of this detector, because there is radiation coming from somewhere that hits this detector. And even if we try now to make this with a very low radiation, it's still radiation. It's the same thing as the nurse at the dentist. She always step out of the room before she give you the X-ray shot. One X-ray shot is probably not a problem, but doing this time after time, eventually it come up to certain values, which might be. So if I now can do this on a safe distance away from this area where you have radiation and just using Bluetooth, it might be a very, very safe option to do it. Of course, you also have the option of having a display that you can do the configuration from. So there is a display on the instrument itself, but it's just for visualization. It's for no configuration, because we don't want anyone to stand here for a longer time to configure an instrument, because we don't know how much radiation do you have here. We do sizing, but sizing is as good as the information that we have received. So this is as well one alternative, and of course also doing with software where you have a laptop and then you connect over a heart modem to the instrument is of course also an alternative way of doing it. All of those things, the three options are available. Other things we also of course look at when you install things. How heavy is it? Can I reduce the weight? Yeah, with today's technology, you can reduce the weight. We can reduce the component size. As you see here, this is the old detector. This is a new detector. I think you have reduced the weight by a principle 50%, because this is stainless steel tubes here. It's also stainless steel head there. So this is of course then easier to install, plus now we have the 4020 milliampere loop powered instrument, which also make it even easier. But just to kind of look at these things, less weight, and by that it's usually easier to install. Otherwise, the active area would be the similar height. We have a photo multiplier that is electronic built in a different way. So how long can those detectors be? Depending on really what is the application. If you're looking at the point level detection, they are usually the active part down here is usually between 8 up to 16 inches in length. Total is probably another 15, 20 inches. So it become something like, I would say, 25, 30 inches length in total. Continuous measurement. Yeah, on the small side, the low side, you can do 8 inches, but very rarely that we see anyone want to measure a continuous measurement of only 8 inches. Usually it's longer. The longest we can do in one detector is 3 meters or 10 feet. Density. There we have the two options of detectors, either the sodium iodide crystal or the PVT detector. They are different lengths, and this have very much to do with what is the line size and what is the density range. Usually when you have line sizes up to somewhere around 8 to 10 inches, then you typically do the 2 or the 4 inch sodium iodide crystal. It will give you a very good accuracy. If you have larger line sizes, then we can use the PVT detector. Yes, it doesn't have that stability, but still it will give you a very good accuracy if you now have a larger line size. And you'll see that maybe later on that we will have some of both of those detectors. So, coming then to another topic that is always of a discussion point when we talk about density, because we need to calibrate. And calibration is typically needed with some kind of media in the pipe. So we will have the source container on one side of the pipe, we have a detector mounted on the opposite side, and now we start to have radiation through the pipe, and we will have a certain attenuation of the radiation, and that will then indicate the density for water. In the past, we would always say that we need to have the pipe filled with first water maybe, and then filled with other media, usually some kind of a slurry. So we have 2 calibration points. I'll skip that one. So we would have this point here for water, which will give us the highest dose rate at the detector. Higher density will attenuate more radiation. So that will be then here. And I now have a lower value of counts. So this was the old style of doing it. The new style is doing it with what they refer to as a smart point. So we still need to calibrate one point. And usually the easiest is to fill this pipe with water. The other point is with the pipe empty. And this could have very well been done first of all. And now we will have this E function curve between those 2 points that will lock the curve. So then when I later on do my measurement, I will have now this curve to follow this E function, and I will then have down here my maximum density without actually having to calibrate this. So this is a significant improvement because I only need to have one liquid, and typically that would be water, and water is very often, at least in the mining applications, equal to 1. So it's a very simple calibration procedure. Now I talked about things in the instrument. Are we going to have some kind of a pull here?
Yes, before we move to applications, gonna ask Gail to load up our second poll. Make sure everyone is still with us. So we want to know what you see as the most important benefit of the Gammapilot FMG50, of the core benefits that we showed. Of course, there are additional features. So a 2-wire loop, powered aspect, SIL, heartbeat technology that we saw with verification and monitoring, or the fact that you don't need additional cooling for applications with hot ambient temperature. So and while we give people a minute, Gerhard, to answer the poll, we have a question that came in about what is the typical range of the Bluetooth signal. I'm going to answer that if you don't mind. I know the answer.
Yeah.
You're safe at 10 meters for sure, 30 feet. I am told that in ideal conditions, we were able to connect up to 20 meters away, so 60 feet. So anywhere between 10 and 20 meters, you'll be able to connect.
Yeah. Endress Hauser is a very conservative company. They are a Swiss company, and they are very conservative, so they usually have suspenders, a belt, and usually also a safety belt to make sure that the pants are not falling off. So we don't publish those numbers as the best. They will probably be more of like on the conservative part.
Yeah, that's why we would say 10 meters, because that's super safe, but you'll probably be able to connect farther within that. All right, the results are in. Yeah, the 2-wire loop power, that's really a game changer. So I'm not surprised to see a strong response to that. SIL used sometimes, but not all that much. Heartbeat, yes, lots of value there. And even, and interesting to see people interested in the fact that it doesn't need additional cooling. So probably applications other than mining that they're doing, perhaps chemical, oil and gas, other things. So yeah, thank you for answering, people. And now we'll have a look at applications.
Okay, so these are Canadian applications where I look to things where I have been. Now let me see what happened now. What did I do now? Oh, there it is. Looks like I did something wrong here.
It was going so well.
Yeah, I know. It's always, do I just flip through here a number of times, or do I go out and kill it? It's a quick repetition of everything that we have seen so far. So.
Yeah, maybe for people who came in a little bit late.
Yeah, okay. Let's now see here where we are. Or is it just that my laptop is booting up here? Okay, no, I went too far maybe. I went too far. Okay, let's now see here. So applications, yes. So these are Canadian applications. In a lot of those, I have been involved, and therefore I show them. Sometimes there is a problem to get pictures, and then I don't have a chance to show them. But anyway, so talking a little bit about where do we see oil, nuclear, and it's oil and gas. We of course have a lot in the oil sands. We do also a lot into the primaries. That is of course also in other applications, but really oil and gas and mining is where we have the vast majority of our applications with nuclear. And of course, when we talk about oil and gas, it's a number of different applications. And I show you the first one that we come across. This is back in 2005. And this is in northern part of Alberta. These are a primary separation cell, which is probably something like 25-30 meters high. And the customer want to measure the interface all across this height of the vessel, because at the bottom there is what they call tailing, which is like the sand and water and so on that they don't really want to have. There is middling, which is the incoming thing from the oil field, and then they inject air and so on, and they get froth, and that skim over, and then it will be the output, which is in principle the oil. What we in that case did, along the side, we installed, or the customer installed, dry wells. We had a number of source containers, I think it was 17 in total, where the isotope was installed in that dry well, and above and below there was detectors, and each detector would then have the density, do the density measurement over a certain range like this, and it would be then the average density, and from there they could then build a profile. And this is just a picture from when they did installation and so on. I also show this -40 because we had a colleague from the factory in Germany coming over and help us, and he was so impressed that he would see -40, and this was displayed outside on the screen that was -40 ambient temperature, and he was so impressed about that. So he actually put it into in this presentation. So otherwise, in oil and gas, very often what we try to do is to do interface between the oil, emulsion layers, and water, and there is different ways of doing this. Very often we will have an isotope installed through a dry well into a certain position in the vessel, and then detectors on the outside. We can of course go across. Going across will mean a much higher source activity, and therefore we try to do this internal sources instead. And in that case, from the outside, this is one of those desalters in northern part of Alberta. Part of the vessel, which is close to 40 feet long, will be outside, and part of it will be inside. When we're looking at the inside, we have already seen this picture. There will be, you don't see the source, but it will coming from the top here in, and then be parked probably somewhere in this area. And then there is a number of detectors on the outside. And this will then create an average density between this detector and this detector and this detector and this detector. And from there, we can then build a profile of what is in really this vessel.
And these, Gerhard, just to quickly mention there, what we see here, that's the older model, the former generation.
Now I did something stupid again. Oh, how do I go out of this now? How do I go out of this? Can I kill? No. Darn it. Oh, I hate this. It's the only way of doing it without shutting everything down. My fault, absolutely my fault. So
let's blame the technology, Gerhard.
I know, but you know, this is something that shouldn't really happen. I mean, the application support, we don't allow these kind of things to happen. So I don't know. It will probably be the penalty box for the rest of the day.
It's because I interrupted you.
Yeah. No, it's no problem. Anyway, so we are back here. So
that's the old model, the 4-wire model. That's what you see all these wires.
Yeah, because I don't have any of these new ones that is installed on these vessels, so I have to live with those detectors and the pictures that I have. Okay, this is another application, but it's kind of talking about temperature, and this is a chemical plant in Quebec where they have between 300 and 500 degrees C inside this vessel here. This is above the floor and this is below the floor, And there's, as you see, no insulation. So on the outside, we can at least assume that this is 150 degrees C at a minimum. The detector is probably something like 8 to 10 inches away, have a water cooling. And this is, of course, if the water cooling doesn't work as it's supposed to, then you kill the detector, which actually have happened in this particular case. And now we need to replace this. And now with a new detector that can take a lot higher temperature, we don't really need to do the water cooling anymore. So that is, of course, a cost saving for that particular customer. I don't have a picture of how that worked with the new detector installed. We do also quite a bit of international projects. And I just show this because this is one of those gigantic projects. As you see here, this is a nickel mine in Ambatovi in Madagascar. And that is number of devices, which doesn't maybe is so impressive. The more impressive is when you see autoclaves like these things. There is very harsh condition in those, and the only thing that we know of that really will work in those applications would then be nuclear. And looking at this will be a dry well as well into here where you put the isotope. These walls here is probably 2 inches of steel, and then there is mortar and bricks and so on. So putting an isotope on the outside going through the entire vessel, you would have more or less an A-bomb on this side. And we don't really want to do that. So this is the solution. And then, of course, this is a lot of engineering where we actually look to how to position detectors in the best possible way. So these are large isotopes, 1500 millicurie of cesium. If we would have had mounting on the outside, we would probably have had a couple of thousand millicurie of cobalt. And I don't really want to be close to that because it will be a lot of radiation. But anyhow, so this was one application that we have done. I was involved in that. This is a gold mine in Quebec. You can see here line sizes 36 inches. Source container mounting on the outside. This is also the old detector on the opposite side. To calibrate this with 2 known liquids like water and a slurry is quite of a bit of an adventure to try to do. So if you now can just fill this pipe with water and have it free also without anything and just do this smart point calibration, it will save them a lot of effort in that case. Other application, this is a diamond mine. This one is in Ontario. There is also those in British Columbia. And there is, of course, smaller line sizes. The challenge here is that they have a lot higher density range. So we need then to calibrate that. In some cases, they also have a pneumatic actuator on the source container to close it in case they would drain this pipe, because then it would be a very high dose rate here on the detector side. And if there is walkways close by, that can then maybe be unsafe for people. So therefore we have this pneumatic actuator there. In other application, which is more far away from where any people would normally walk, they just have manual actuators on those source containers. And a completely different application is weight scale, which has a screw conveyor hidden inside here. This is a retrofit where this company bought a nuclear device many years ago. This is an old source container from another vendor. And when their detector was not sensitive enough because of the decay of the isotope, then they come to us and asked if we could do something. We went there and we measured the radiation that was present. And they said, yeah, we can do this. And then we installed just one of our detectors. In this case, it was of course the previous year version with the 4-wire device.
Just a quick time check, Gerhard. We have a couple of questions to answer, and we have about 2 minutes left. So you have a bit of a challenge too.
So let me ask to finish this, because this is now, and this is then another application where we do replacement, density. As you see here, these are old detectors that the customer actually kept. These are a lot less sensitive than what detectors are today. So the last thing that any customer want to do is to send a nuclear source for scrap, because it costs money, it's a lot of paperwork involved. What they want to do is just to reuse this isotope that they had and then put in a new detector that is more sensitive. The original source was installed 1992, so start to be really old, and these old detectors were not able to be capable to do the measurement anymore, so we replaced those with our detectors, and the customer could then continue to operate without actually having to exchange the isotope. That is something that we can do easily. There is usually a mounting bracket that is provided with each vendor's density gauges. We will then just remove the detector, and then the detector is typically attached with 4 screws in square, usually 6.5 or 6, maybe sometimes 7 inches apart. And we just have a plate, we put our detector on that, and then put that instead of the old detector, and then we can usually without any problem start up this operation. So to summarize this a little bit, we do point level, we do continuous measurement, we do density, we do interface, and of course now with the new detectors we have this feature of loop powered. Of course it has cell, it have the heartbeat. You can do a lot more things without actually having to have any kind of cooling. There is detectors up to 3 meters in length, Bluetooth, very good feature, and of course Gerhard Jansson, reduced size and all of these things as we already talked about.
Okay. Well, we're out of time, so questions came in, we'll answer them via email for everybody to have a look at. Just want to quickly mention we have an exciting event coming on December 1st. You will have received an invitation by email or seen it on our social media or even on our website. Make sure you sign up for that. Great webinars, great content from all the product management people, from R&D, on all our different families of products, technologies, industries we work with. So December 1st, make sure you sign up for that, and you'll be able also to have a look at our 3D virtual booth. Actually, you can go in today through our website endress.com and see that virtual booth. But on December 1st, yes, and you'll get all the previews also of products coming in 2021, and a chance to network with people from E&H, ask your questions, talk with our experts. So make sure you sign up for that. Thanks for joining today. Thanks for your time, for your attention, for participating, and we'll see you next time. Thanks, Gail. Thanks, Gerhard.
Thanks.
Thank you, and have a nice afternoon, everyone.